fix this real quick. Now, hello there, hello there, hello there. Now you can hear me? I think so. Okay, great. Okay. Okay, guys. So hello everybody. Welcome to this live class number 103, where we are going to be talking about Kalman filters. So let's start. Alright, so hello everybody, welcome all the ROS developers that you are here. I see that there is many people today in this live class, so welcome everybody. My name is Alberto, and today we are going to be doing a live class where we are going to be talking a little bit about Kalman filters, and especially doing some practical exercises with a TurtleBot in a gazebo simulated environment. So, well, I think now everything is fine, the image should be fine, also the sound. Let me know in the chat if everything is fine. Can hear now? Yes, we hear. What are Kalman filters? You are going to see now what are Kalman filters. Cameron, see it now. Yes. Hello everybody. Okay, great. So well, let's not lose any more time and let's start. So as always, what I want to do, what I am going to do first is to share with you the project, which is the one that we are going to be working with today. And for that, let me quickly switch to my computer screen. So let me switch here to my computer screen. Okay, and as always, I'm going to start here by, well, let me grab this. This fork is outdated. Let me grab the latest changes here. Alright, so then let me real quick grab the link here, and I'm going to share it here in the YouTube chat so that all of you guys can have it. So let me just paste it here real quick. There you go. Okay, so now what should you do with this link? Then with this link, what you have to do is to click it or copy it and paste it into your browser, of course. And then, by doing so, what you are going to do is to have this project, this Kalman filters project for the ROS developers live class number 103. You're going to have this project into your workspace of the ROS development studio. Yes. If you have already been in previous live classes, you already know all this, but probably we have new people today. So let me explain it again. So we are going to be working in the ROS Development Studio. Then if you don't have an account, just create it. It's going to take you a few seconds and it's completely free. Then once you create the account and you are logged into the ROS Development Studio, and you copy paste, for instance, the link I have passed to the chat here, then you are going to automatically have a copy of this project into your workspace. Yeah, makes sense? Then what to do? So once you have the project into your workspace, all you have to do is to click here in the open button and open project. Yep. Then this is going to start loading the environment, the development environment for you. It might take a couple of minutes, up to a couple of minutes. So let's just be a bit patient. Then meanwhile, let's have a quick chat as always. So yeah, today we are going to be talking about Kalman filters, but we are going to have a little view, let's say, yes, just a preview, because Kalman filters is a huge thing. Then we are going to have a small peek today, But why are we going to be talking about Kalman filters? Well, first of all, because it's a very important topic in robotics, yes, in general. And also because we are going to be publishing a course, a complete course on Kalman filters next week. Yes, so this live class and this project is going to be a preview of the contents of that course. Yes, now when we start reviewing the notebook, we are going to see that it's just a small preview. Yes, there are some things missing. Also, we are limited in time. We only have 1 hour, so we cannot explain everything. So yeah, we are going to publish a full Kalman filters course in our academy. Yes, then also for the ones who already know about our academy, you may have noticed that this week we have done a major update to our academy. Yeah, let me come here. So we have done a major update to our academy. Yes, many new things here. We are still, this is the first days that we have, basically we published this new academy on Sunday, so you may still find some books, whatever, but I want to say that this academy, in my opinion, is much better than the one we had before, and it's going to keep improving, so we are going to keep improving on this one. I hope you will have a great experience with this new academy that we have published, and remember that next week we are going to be publishing this Kalman filters course and probably others. Yes, there are other courses to come, like for instance a course on robot dynamics, super interesting, another course on arm kinematics, which is the topic that we did the live class in the previous week. So many new things coming to this academy, so stay tuned. Yeah, so let me shut up now and let's come here. So great, so now as you can see, my environment has loaded, and here I have automatically opened my notebook for today's live class. Yes, so did all of you guys open the notebook? I can see Elder saying, really nice interface, got much better. Thank you, Elder, the Elder camera. Yeah, so our goal is to keep improving each day. This is our goal. So keep improving each day, each week, each month, etc. So thank you very much for your comments. Yes, loading. Okay, so for most of you has loaded, for some of you is still loading, but it's going to load in the following seconds, minutes, so don't worry at all. Then, okay, so what are we going to do? Well, so here we have the Jupyter notebook for the ROS developers live class number 103. Then basically what we are going to do is to follow the instructions that are written here into the notebook. Yes, so all I'm going to do is to follow the instructions with you at the same time of this Jupyter notebook. Yes, there are some theory parts, there are some practice parts, but I'm going to basically be following the indications that I have written here into the notebook. Yes, so what do I want you to do? I want you to do the same that I do. Yes, so I don't want you to stay there behind your computers listening to what I am saying. Yeah, I know I have a very, very nice voice, but I don't want you to be just listening to my nice voice, but I want you to be practicing with me. Yes, so everything that I'm going to be doing in my project, you are going to be able to reproduce it exactly the same in your computer. Yes, then this is what I want you to do. Then there is the possibility that at some points you get lost. There are some things that you don't understand very well. That's normal. Yes, then don't worry, because after this live class session finishes, we are going to publish the full video into YouTube, so that you are going to be able to review it, and also you are going to have forever this project in your workspace. Yes, so you are going to be able to open this project tomorrow, next week, next month, whatever, in order to keep practicing and keep having a look at the instructions, whatever you want to do. Yeah, so let's start then. The first thing to do here is to set up the simulation environment in this case. Yes, so for this, well, first of all, let me just have a quick look here at the requirements. So a couple of basic requirements that you need, not only for this live class but for all the live classes, is to have a minimum knowledge on Linux systems and a minimum knowledge on Python programming. Yes, so both of these you can get them in our academy as well as free courses. You can see them here: Python 3 for robotics and Linux for robotics. So you have these two courses which are completely free. You don't need to be subscribed or anything in order to do these courses. So in case you would like to improve your Python or Linux skills, or in case you don't have any idea of this, I highly recommend you to have a look at these courses, completely free, as I've said. Alright, so having said all this, let's start setting up our simulated environment. So for this, what we are going to do is to start launching the simulation. How? Well, we are going to come here to the simulations panel. Then here we are going to choose the choose launch file button. Yes, this is going to give us a list of all the available launch files that we have in this project. Yes, then from all the launch files and packages, we are going to select the empty turtlebot.launch file from the TurtleBot gazebo package. Yes, so let me come here, click on the button, and then here I might try to search for the TurtleBot gazebo package, which I have here, and inside here I'm going to select the empty_turtlebot.launch file. Yes, so I have selected this file, and then I'm going to click on the launch button. So this is going to automatically open here a gazebo window, and it's going to load the simulation, which as you can see here, it's starting to load. And if everything goes fine, we should end up with something like this. Yes, with a TurtleBot robot here in an empty world. So let's wait a few seconds until the gazebo simulation loads. There we go, here we have it. Here I have a book here in the ground because I'm getting it white. In this case, I can just refresh here the window so that it gets rendered again. And as you can see, the textures and everything, it's loaded properly. Excellent, so now I'm ready to start. So I'm basically set up to start with the live class. So let me ask a last question. Let me know if all you guys have your project loaded with the notebook opened here at one side and with the gazebo simulation already loaded and started. Yes, I want you to be here at the same point as I am so that we can keep moving together. So let me know, guys, in the chat if you are here at the same point as I am. Hey, yes, all set. Yes, done. Same point as you. Yes, simulation and notebook are set up. Done. Already. Ready. Done. Okay, excellent. Excellent. So then let's start. Let's start with this. Okay, so before going into the Kalman filters section, which is the main point of this live class, let's briefly introduce a couple of concepts. One is the bias filter. So what is a bias filter? Well, let's explain it like this. So let's dissect the term of bias filter. First, a filter applied into a process is something that takes noise, uncertainty out of an input to get a more accurate estimate as an output. Yes, so this is basically a filter. Takes noise from an input to get a more accurate output. Then the term bias is applied because concepts from Bayesian statistics are involved. We are not going to go deep into this. You have some links here that you can check in case you are interested. Then in Bayesian statistics, past information is taken into account in order to generate estimated values under uncertainty. So let's say that a bias filter is an estimation algorithm that uses past values in order to provide a more accurate estimate output. Yes? So this would be in comparison to an algorithm that does not consider past values. Yes, so this is a very simplified version of a bias filter. Then, okay, but this live class is about Kalman filters, right? So why I am talking about bias filter? Well, Kalman filters is a special case of a bias filter. That's why. Yes, so the Kalman filter will go into the group of Bayesian filters. Yes, then understanding the general Bayesian filtering algorithm is essential to understand the principle on which other members of the family, like the Bayes filter, work. However, as I've said previously in the introduction, in this live class there's not much time available. We have only 1 hour, so we are going to skip this part, the part where we go deep into the Bayes filter, and we are going to jump directly to the Kalman filters. Yes. However, let me tell you that in the complete course that we are going to publish next week, you are going to have a full unit only about Bayes filters. Yes, which is going to be a much more detailed unit on Bayes filters. Yes, which is going to help a lot in order to better understand Kalman filters. Yes. However, as you may understand, in this live class we only have 1 hour. In fact, less. We have currently just 40 minutes. So we cannot explain everything. Then we are going to skip this Bayes filter and jump straight into the Kalman filter. So as for the Bayes filter, just keep in mind that it's an algorithm that uses past values in order to provide a more accurate output. Yes, and that the Kalman filter is a special case. It's inside the general group of Bayes filters. Yes. Then another thing I would like to introduce here as an introduction is the Gaussian distributions. Yes, so a Gaussian distribution, also known as normal distribution, is a continuous function that is often called the bell curve, because the graph of its probability density looks like a bell. We are going to see it now. Then a very interesting fact in Gaussian distributions is that they can be fully modeled using only 2 parameters, the mean, mu, and the standard deviation, sigma. Yep. So this Gaussian distribution can be modeled using only 2 parameters. So let's do again, so we are not going to go deep into Gaussian distributions because it's too much. Yes. Then let's do a quick exercise here, a quick practical demonstration to see how the shape of Gaussian distributions changes with different values of mu or sigma. Then here we have an example code which is going to basically generate a histogram with a Gaussian distribution. Yes, then what we can do here is to tweak the parameters mu and sigma and see how the histogram and the Gaussian distribution changes. Yep. So here you have an example code which is going to basically, as you can see here, we are initializing the mu and sigma values. Here we are generating an histogram. All of this is Python code, so it's pretty simple. Then here we are generating the plot, showing the plot, generating the grids, etc. So if we come here and we run this cell, we select this cell. Yes, if I do a left click here with the mouse, you are going to see that this cell is going to be selected. It's highlighted here with a blue border. Then once it is selected, I can click here on the run button, and this is going to start executing this Python code here, and it's going to generate a histogram, this histogram with the Gaussian distribution. So let's wait a few seconds. The first time we execute it, it might take a bit longer to load because it needs to import everything and initialize everything. As you can see here, we can see an asterisk, which means that it's being executed yet. Now it has finished, and here in this case, as you can see, I get a message, but I don't get the histogram. Yes, I get only a message. In this case, just let's select the cell again. I'm going to select the cell again and execute it. And this time, you're going to see that it's going to be generated super quickly. Yes? So here we have the histogram, yes, which are these bars here, these green bars, with the Gaussian distribution function, which is this red line here. Yes? Then, so now what we can do, for instance, you can do it later if you want, we can see that by modifying these mu and sigma values, let's set here 20 and 35, for instance. If I execute again this cell, you're going to see that this histogram is going to change. Yes, so there we go. Yes, so now we have as mu 20 and a sigma 35, and now we can see, for instance, that these values, the values, has changed. Yes, Okay, so let's, this is just a simple example in order to see and play a little bit with this. So let me just set it back to the value. So for instance, here you can see that the function starts more or less at minus 100, and if we change again the values here and we run it, we are going to see that these values are much lower. Yes, so you can play a little bit with this. We can analyze a little bit the code if you're interested in. Yes, but well, here we are just introducing Gaussian distributions. Then, so far so good. Okay, so what if we build a bias filter that works with Gaussian distributions? Then, in order to do this, we will need to adapt our initial state, predicted step, and corrected step to work with Gaussians. Or, in other words, we will need to build a Kalman filter. So, in fact, the Kalman filter is a special case of bias filter, as we have just said, where the following conditions are met. The first condition is the state space is continuous. Yes, so in a bias filter, the state space is discrete. Then the motion model is linear Gaussian. Linear in its arguments plus Gaussian noise. The third condition is that the sensor model is linear Gaussian, and the final condition is that the initial state probability is Gaussian. Yes? So basically, a Kalman filter is a special case of bias filter where the following conditions are met. Yeah, so basically it's applying Gaussian distributions to a bias filter. Yeah. So that's why I first introduced the bias filter and the Gaussian distributions. Unfortunately, we don't have much time in this live class, so we cannot go deep into this. But as I have said, in the course we are going to publish next week, we are going to have this much more explained, especially the bias filter part. Yes. Then, okay, so let's just skip the introduction and let's start with the Kalman filter itself. In this case, we are going to start with the one-dimensional Kalman filter. Why one-dimensional? Well, because there are multi-dimensional Kalman filters. In this live class, we are not going to explain them because it's too much. We are going to focus only on the one-dimensional Kalman filters. But in the course, we have also included all the section with the multidimensional Kalman filters, etc., etc. Yes, so that's why at the beginning I said that this live class is just a preview of the course. So let me get 1 second because I'm talking too much without stopping. So I need here real quick to get a drink because otherwise I'm going to die here or something. All right, let's go back to working. All right, then there we go. So one-dimensional Kalman filter. Then a closer look into our simulated environment. So here we have our simulated environment with an empty gazebo world and a TurtleBot 2 here spawned in the middle of the environment, of the space. Yes. So in this case, what we want to do is to focus 100% on the Kalman filter part. Yes, because it's what this live class is about. So therefore, we are not going to focus that much into explaining ROS concepts like what is a publisher, a subscriber, etc. So that's why we have basically prepared here a code which is going to launch some auxiliary ROS nodes that are going to help us in our explanation. Yes. So basically, what it's going to do is to adapt the sensor's data for the exercise. For instance, we are going to add some noise to the odometry and laser sensor in gazebo, among other things, yes? Then in order to start and launch these auxiliary nodes, all we have to do is to execute this command. So let's come here to the tools, open a new shell, let's put it here, and then we can copy and paste this command here, and this is going to start. It's going to spawn here a wall, you are going to see, and it's going to start automatically moving the TurtleBot here. There we go. Yes. So here we have launched our auxiliary nodes. So we should see something like this, and we should see that the robot travels at constant speed in a straight line. When it reaches the position x equals 10, then it gets teleported back to the position x equals 0 and continues moving forward as before. So we can see here this behavior, yes? So the robot starts moving forwards towards this wall, and when it reaches the position x equals 10, which is around here, then it gets teleported back to the position x equals 0, and then it goes over again. Let's see how this happens, and there we go. Yep, okay, so we have this environment working properly. Then, the topics that we will require are the following: noisy odom X, position from laser ray, and ground truth X. So these topics are provided also by our auxiliary nodes, which are some position from the laser ray with some added noise, the odometry with some added noise, etc. Then let's verify and let's make sure that these topics are being published so that we can keep working. And for instance, we can do a ROS topic info of the noisy odom X, and we can see that in fact the topic is being published here by this node, by the odom utility tools node. So far so good. We should also verify with a ROS topic info, for instance, that the position from laser ray is being published, which it is. And finally, we should check that the ground truth X topic is also there. Okay, so all the topics are being published, as we can see here, are there, so we are set up, yes? Also, let's take a moment to verify that this simulation satisfies the conditions for a traditional Kalman filter, which are the conditions we mentioned before. So, first, linear movement. The robot moves in a straight line and at constant speed, okay. Linear sensors. All sensor readings are published in the map frame of reference, same as the robot position, okay. And Gaussian noise. Both odometry and position from the laser scan reading have built-in Gaussian noise. Okay, excellent. So all the conditions for a traditional Kalman filter are met in this environment. Yes? So, excellent. We are ready to start working and creating our Kalman filter. Yeah? Then remember to leave this program executing for the wildlife class. Yes, the one we have just executed. We need to leave it here running. We can minimize it. You can minimize it if you want, whatever, but don't stop it. Yes, so you need to leave it here running, because this program is the one which is providing us all these topics, which we need them in order to create our Kalman filter. Yes. Also, this program is the one which keeps moving the robot here at a constant speed, etc. Yep. So don't close it. Just minimize it if you want. You can forget about this and leave it there running in the background. Yeah. I'm going to do so. I'm going to minimize it here. All right. Then let's start. So filter initialization. Then the very first time the Kalman filter cycle is performed, the prior belief corresponds to the initialization values of the state mean and variance. To represent the situation where the robot could be anywhere in the state space, the mean can be initialized as a random number within the state space and the variance as a very, very large number. For instance, the state space to the power 3, as an example. Then, for this live class, we have written here a template, a boilerplate code for the Kalman filter node in ROS. Then, to add the initial state, you just have to fill in the required code. Then, inside the code editor window, open the ls103 folder located inside Katkin Workspace SRC. Then, the code editor. Where do we have the code editor? We have it here in the tools. In the IDE, here we have the code editor, where we are going to be able to work and edit our files with a graphical tool. There we have it. Then here it tells me to open Katkin Workspace SRC, which I have here, Katkin Workspace SRC, and inside here I have the LSLC103, which goes for live class 103. Then inside this folder I have this Kalman filter.py Python file. Yeah, so far so good. Then, step 3, paste the code block below where indicated by the comment paste initial state here. So basically here it's asking me to paste this code into this Kalman filter py. Let me open it. There we go, okay. Then here somewhere we have this paste initial state here. Let's, here we have it, at initial state here. Then under this comment, under this line here, we should copy these lines here, these lines of code. So let me copy and paste them here, and there we go. So basically here we are initializing the mu and sigma values, yeah? So we are adding the initial state of the Kalman filter, yes? There we go. Yes, these are the mu and sig and sigma values that were introduced as well before here when we explained this Gaussian distribution, yeah? So this is going to set up the initial state for our filter, yes? This is the first thing we need to do. We need to initialize the filter. Okay, next thing. Next we have the correct step. So in the correct step, we create a new belief about the robot's location, about the robot's position, based on the laser ray sensor reading, and combine it with the previous belief we had. Yeah, so we are going to listen to the laser ray sensor reading, and then we are going to combine it with the previous belief we had about our robot's position. Yes, so here we have the initial state, and then we measure, we get the laser reading, and we can update the initial state of the robot. Yes, so you can see the robot's position belief updated after sensor measurement. Then, in the discrete case, we've learned that in this case we have learned, because this is explained in the bias filter unit, so we haven't done it, but in the discrete case, the update step is the multiplication of likelihood by the prior belief. Then it turns out that the same formula also applies when working with continuous state variables. Yes? So in case we are working with continuous state variables, which is the case of the Kalman filter, the same formula applies. So this correct step can be measured as the likelihood multiplied by the prior belief. Then the likelihood for discrete distributions, calculating the likelihood requires finding the probability of the measurement given each and every state. Again, here we are talking about the discrete case, which is the bias filter. Then in a continuous probability distribution, which is the Kalman filter, the probability of the measurement given the current state is provided by the Gaussian distribution of the measurement model of the sensor. Then you can verify that by yourself using the general formula of Gaussian function, whatever. Okay, for instance, our laser sensor can be modeled as a Gaussian distribution with mean and variance sigma power to 0.04. If we get a sensor reading indicating a robot position at x equals 5, we could calculate the probability of the robot being at any other value of x just using the general formula for a Gaussian function. Yes, here we have some theory concepts. I'm not going to go too deep into this for now. Let's just keep moving. Then, prior belief. So we just saw that for the first Kalman filter cycle, the prior belief corresponds to the initialization values of mean and variance. Yes, here we are talking about these values that we have initialized here. In every subsequent filter iteration, the estimated mean and variance of the last estimation are used as a prior belief each time a new measurement is received. Yeah, so each time a new step takes place, the prior belief changes. Yeah. Then, so since likelihood and prior belief are both Gaussian distributions, the next question is, how do we multiply Gaussian distributions? Then, fortunately for us, the formulas have been worked out by mathematicians, but very smart and genius of mathematics, and we just need to implement them. We can directly use them. Then the new mean, we can get them with the following formula, and the new sigma here, the new variance, we can get them with the following formula. Yes, where we have prior mean and prior variance with our mu sub 1 and sigma power 2 sub 1, and we have the measurement mean and measurement variance, which are the mu sub 2 and sigma power 2 sub 2. Yep. So here we have some theoretical mathematics. Let's not start analyzing this too deep, because we don't have time for that. So just you can have a look later at all these formulas. You can open also here the links that we have I have shared here in order to better understand this. Then, by looking at the equations, we can see that the mean of the resulting posterior belief is a weighted average of the prior belief mean and measurement mean normalized by the sum of the weighting factors. Yeah, so here we're describing this formula here. Then, consequently, the probability density function with the smaller standard deviation, less variation, equals more precision, is weighted more. Then writing those math formulas as Python code is straightforward. Yes, so basically here what we are doing is to transform these two formulas, the new mean and the new variance. Yes, here we have the new mean and here we have the new variance. We are writing these formulas into Python code. As you can see, they can be written into Python very easily. Yeah, so straightforward, in a straightforward way. Then let's keep working with our code. So then let's go back to our code editor. Then inside the code editor window, let's open again the LC100C folder, and let's open the Kalman filter file. Here we already have it opened. Then let's paste the code block below where indicated by the comment paste measurement update function here. Yes, this is wrong. It's not measurement update, but correct step. Yes, you can modify it here if you want in the notebook. Yes, so paste correct step function here. So we should come here to the code, and here we have this comment section which says add correct step function here. Yes, this is the one we are looking for. So below this comment we should copy and paste this code here. Yep. So here we have the correct step function definition. Yes. What are we doing here? Well, basically what we are doing is to apply these two formulas. Yes, these two formulas that we introduced here and that we written here in Python. Yes, so we are basically adding these two formulas, the new mean and the new var, as Python code here, and then we return the new mean and the new var in the correct step. Yes, all right. So we have added the correct step of the Kalman filter into our Python code. So far, so good. There we go. Okay. So yeah, then the update step is the multiplication of prior belief by likelihood, and it's as simple as the multiplication of two Gaussian distribution. That was easy. Then let's move to the prediction step. Then the prediction step of the Kalman filter is the second half of the Kalman filter cycle. It is the estimation of all the possible robot positions after moving, considering that the robot movement is uncertain. Then let's pick up where we left off. After taking the measurement into account, we got a new Gaussian distribution. It is the current best estimate of the robot's location. Now in the movement update step, which is this step, it's the correct step. I got lost now. Okay, yeah. In the movement update step, the robot moves forward. Then we represent the robot motion as a Gaussian distribution because the new position is not certain. Yes, we can see an image here where we have the previous step, and this is the new, position of the robot, which is uncertain. So it is represented as well as a Gaussian distribution. Yes, which is this bell function that we talked before. The resulting position after the robot motion is less precise, as shown by a flattened Gaussian distribution. Yes, so here we have a more precise Gaussian distribution, and here we have a less precise Gaussian distribution. So, how do we combine the Gaussian distribution of the location estimate before the movement, which is this one, with the Gaussian that represents the robot movement, which is this one? Okay, so we do so by combining both Gaussian distributions simply by adding both means and variances. So the mean of the sum of two normal distributions is the sum of their means. Super easy, yeah? Then the variance of the sum of two normal distributions is the sum of their variances. Also super straightforward. Then the new mean and the new variance will form a new Gaussian distribution, which written in Python, yeah, here we have these two functions written in Python. Yep, super easy, super straightforward. Yeah. Then inside the code editor window, let's have a look again at the LS103 Kalman filter code, and now we are going to look for the state prediction, which I think also it's not named like this, but it's predict step. Yeah, it's predict step. Let me change it here in the notebook as well. Yeah, so let's look for this predict step comment here. Yes, here we have it. In my case, I have it right here, right below the correct step. Add predict step function here. Then in here, what we are going to do is to copy this code and paste it here. Yes. Then here, basically, what we are doing, as you can see, is to calculate the new mean by adding the two means, and the new var by adding the two vars of the Gaussian distributions. Yes, and finally we return the new mean and the new var, the new variance. Yep, so super straightforward. So now, in order to finish our template, let's complete our filter by placing a call to the measurement update. And okay, this is wrong as well. This is, sorry for this, this is correct. Step and predict step. Yes, the functions are correct step and predict step, which are the two functions that we have created here. So what we have to do is to place calls, because here we have just defined the functions. Yes, we have defined this function correct step, and we have defined this function predict step. So now what we need to do is to basically call these functions. Where? Well, we are going to call these functions inside the odometry callback function, so that each time a new odometry reading is received, a new iteration of the Kalman filter is executed. Yeah. So let's copy the following code, in this case in the past Kalman filter cycle here. So let me look for this, which we have basically here. Add Kalman filter cycle here. Yeah, here I have this comment. So now what I'm going to do is to grab this code here, copy it and paste it here. Let me fix here the indentation. We need to, okay, there we have. Yeah, super important to pay attention to the indentation. Yes, because in Python the indentation here of the code, it's super important. So pay attention to this. Yes, make sure that the indentation of this it's the same as this one. Yes, not of this one but of this one. Yep, super important. Then, okay, so what are we doing here? Well, basically we are calling the predict step, which we have defined here. Then we are printing, using the ROS by log info function, we are printing the mu and sigma values of this predict step, and then we call the correct step, which is this second function, this first function, sorry, we call the correct step, and then we print the resulting mu and sigma values. Yes, make sense? Okay. All right, so we have written our code. Yeah, so here we have everything. What is this? Okay, so let's have a quick overview here at the code. Let's not go too deep into it, but here basically we are importing the ROS-Py module. We are importing the float 64 ROS type message, basic. We are defining some global variables, which are the last odom position and last measurements, which we initialize to 0. We define here, we are initializing the state. This step we did it together, which is the mu and the sigma. We are initializing the state of the Gaussian distribution. Here we are initializing the motion sigma, motion sig, and the measurement sig. This time since the last filter cycle, we are initializing some variables that we are going to use here in the program. Then we define here the correct step and the predict step, which are the steps of the Kalman filter, the two steps of the Kalman filter, the traditional Kalman filter, which we have seen. Basically here we have the functions that we have introduced here. Yes, the different functions that we have introduced here are contained here in the two functions that we have created in Python, which are the correct step and the predict step. Yep. Then we have the odometry callback. Yes, so this is a ROS, the callback of a ROS subscriber. So every time a new odometry message is published by the robot, this function is going to be called. Yeah, so here basically then we are initializing, well, not initializing, but calling all the global variables here. And then inside this callback, what we do here is to measure distance since the last filter cycle. And here is the most important part, the part that we have just added, which is to place here the calls to the predictor step function and to the correct step function. Yes? And here we keep the data of the odometry for the next filter cycle. We publish the mu here, so we are publishing the filtered position, the resulting position from the Kalman filter. We are publishing it here into a topic that we are going to see here. Yeah, here we have the topic where we are publishing the filtered position, the output that the Kalman filter gives us. Yes, and we are going to visualize it here in next step. Yeah. Then here we have also the callback for the laser, and here we have the main function, where basically when you take the node, we subscribe to the odometry with the noise, with the Gaussian noise. We subscribe to the position from laser array also with the Gaussian noise. Remember, these two topics are provided by the program that we started at the beginning. Yeah, by this program that we have here running in the background. And then we generate also a publisher, which is going where we are going to publish the filtered position, so the output we get from executing the Kalman filter. And that's it. So basically that's it. Yes, you can analyze if you want more in depth later this code, modify it if you want, whatever. So yeah, so here we have ready our code for the Kalman filter, for the one-dimensional Kalman filter. Then what else? Okay, so we have our auxiliary nodes running. Then let's test this program. So let's test it with the following command. Then I'm going to come here and run this program. And this is going to gives us to generate an output similar to this, where we have the mu. Yeah, so here we have the values from the correct step and the predict step. Yes, these are the log infos that we are using here. So we have the mu and the sigmas from the predict step and the correct step. Yes, here we have them. So this is nice, but what if we try to visualize them here in a more graphical way, which helps us understand better what the Kalman filter is doing? Yes, so yeah, this is super cool and all, but what's so great about the Kalman filter? So one way to figure out how the filter is doing is by looking at the filter input and output data plotted on a graph. Yes, so that is exactly what we are going to do now, and what we are going to be finishing with this live class. Yes, so let's also now keep this program running. Yes, we need this program running because it's the one that it keeps running and iterating over the Kalman filter. So I'm going to minimize it here, and I'm going to open a new shell. Now in this new shell, what I'm going to do is to execute RQT-plot. Yep, RQT-plot is an application that ROS provides, which generates plots, as the name itself says. Yeah, so it's going to allow us to generate plots from topics data. Yes, so since we have all this data published into topics, we can generate plots from this data using this RQT-plot. Now here we have launched it, but in order to visualize it, we need to open the graphical tools. So let me open here the graphical tools, and I'm going to click here in the first icon in order to move it to a new tab, so that it doesn't take much space here. And here I have it. I'm going to double click here in order to maximize it. There we go. So here I have RQT-plot opened. So what I'm going to do here, okay, the first thing I'm going to plot is the noisy odom X topic. So for this, all I have to do is to come here and start writing the name of the topic, which is noisy. And as you can see, as I start writing it, it shows me here the option to autocomplete it. So I'm going to select it. Then once I have it here, I'm going to click here on the plus button, and this is going to add the data of this topic into this graph. So let me click here on the plus button, and now here I'm going to start seeing the noisy odom X topic data. Here I have it. Okay, next, let's also plot the position from laser ray topic. So let's come here and introduce the name of this topic and autocomplete it, position from laser ray, and finally click on the plus button, and now here I have in red also the data from the position from laser ray topic. And finally, you can add as many topics as needed, each time typing in the topic name and pressing the plus button. So finally, what we are going to do is to plot in RQT plot the topics noisy odom and position from laser ray, and observe the plot while the robot moves. Yes, so here the plot keeps moving, and we can see we have the data here. Here we have the initialization, and we can see that we have the noisy odom X data. It's doing a kind of zigzag, as we can see, and we can see also a lot of noise here in the position from laser ray data. Yeah, so in both of them we can see that there's quite noise. Yes, because the robot is moving continuously, and here we are seeing a lot of variations. So notice that the x-axis represents the timestamp. The y-axis, which is this one here, indicates the robot pose in X published by each topic. So this value will start at 0 and move upwards until 10 as the robot moves forward in a straight line from xy 0, 0 to xy 10, 0 in the map. Yeah, so the robot is going to start at the x0 position and move until the x10 position. Yes? A zigzag kind of line, such as the position from the laser scanner, shows the fluctuation due to the sensor's noise. Yep. So here we can see how the position starts at 0 and it keeps increasing. It keeps increasing until it reaches 10. Yes, this should be the expected behavior. But as you can see, the behavior is quite strange. We can see that the red data, the data from the laser, it keeps going up in a more or less continuous way, but still we have noise, especially at the beginning. You're going to see now that when it initializes, it has a lot of noise. Yes, and the same with the noisy odom, which has a lot of noise. So now what we are going to do is to add to this graph the filtered post topic. Why this topic? Well, because this is the topic that we are publishing here. Yes, this is the topic that we are publishing here, which contains the output of the filter. Yes, so the output that our Kalman filter is calculating is published here into this topic. So basically, here we are going to visualize the Kalman filter output. So let me select here the filtered post. There we go, and let's click here on the plus button in order to add the filtered post topic. And there we have it. So we can see it here in light blue color. Yes, we can see it goes very close to the red line, which is the position from the laser, but it's much more smooth. Yes, you can see that the light blue line is much more smooth than the data that we are getting from the laser ray. Yes, so this is the magic of the Kalman filters. Yes, so it's helping me to filter all the noise that in this case the position from the laser ray data has. Yes, so this is the magic, and this is the main use of Kalman filters in robotics, and in this case in working with ROS. Yes, so it takes a noisy input and it produces a much more smooth output. Yes, so yeah, can you see how the position from the laser scanner is very noisy? Do you notice how the position from odometry is susceptible to drift away over time? Then the filter result is both smooth and significantly less sensitive to the odometry drift. We can finally we can also plot here the ground truth if you want. I'm not going to do it, but you can do it if you want in your case. And also as a final note, so note that some drift in the filtered estimate is inevitable. Yes, but this can be further corrected with a global positioning algorithm such as the particle filter or the AMCL. If you have worked with ROS navigation, this might be familiar to you. The AMCL node, which is the adaptive Monte Carlo algorithm. Yes, so this can be further corrected. It can be applied to improve the this data. Yes, which, by the way, the particle filter is going to be studied also in one of the units of the Kalman filters course that we are going to publish. Yes. Obviously, we don't have time here, so basically we have reached the maximum time right now. So, but remember that in the course we are going to have much more than this. So we are going to have a unit dedicated to bias filter. We are going to have a much more extensive unit for Kalman filters, including, for instance, multi-dimensional Kalman filters, which we haven't explained today. We have other units as well for extended and extended Kalman filter, extended Kalman filter as well, also for the particle filters, etc. Yes, so keep in mind that this course is going to come to the academy next week. So yeah, that's all from my part. So we have been able to create here from zero. Well, we used a template. We provided here a template in order to make things a little bit easier. But yeah, we have basically created here a basic Kalman filter from zero, applying it here to a gazebo simulation with the TurtleBot, and we can see here, which is super interesting, how the output is much more smoother than the noisy input, which is basically the main purpose of the Kalman filter. So yeah, that's all for today's live class. I hope you have enjoyed this live class. You have learned something new. In case, let me switch here to my very pretty face. So in case you missed some part, in case you would like to review, remember that once this live finishes, now we are going to, well, in maybe 10 minutes or something like that, we are going to publish this live class as a regular video into YouTube, so that you can visualize it again if you want. And also remember that you are going to have this project that we have been working with today. You're going to have it forever in your workspace. Yeah, so you can come back to work with it tomorrow, next week, or next year. Whenever you want, you are going to have this project in your workspace forever. Yes, in case you want to reproduce the steps again, whatever. So yeah, guys, thank you very much for being today with me. I can see that today we got a lot of people, so thank you very much. Almost 200 people, I think, that we had at some point. So thank you very much, guys. Thank you. This was very interesting, says Engineering Nations. Thank you, Engineering, for being always in all our live classes. You don't miss a single one. So thank you very much for your support. Is AKF included in the course? Yes, it is. It is, Pratyush. AKF and UKF are included in the course. Thank you, Alberto. Great class as usual, says Lucas. Thank you very much, Lucas. Maxime, Magracea Tech Solutions, Yehor, Helder Camera. Thank you very much, guys. So thank you very much for your kind words. You are all saying me thank you, but thank you for supporting us and for being here in these live classes. Because without you, obviously, these live classes wouldn't happen. Yes, it won't be very interesting to be doing these live classes with zero viewers. So thank you very much, guys, and I will see you next week, where we are going to start doing live classes on ROS 2. So stay tuned. Yes, we are going to leave a little bit these more theoretical concepts like arm kinematics, Kalman filters, robot dynamics, etc., and we are going to go back to ROS 2. So if you are interested in ROS 2, stay tuned, because the next live classes are going to be on that topic. Yes, ROS 2. So thank you very much, guys, and see you next week. Until then, take care and keep pushing your ROS learning. Bye bye. What are you doing, Alberto?
I'm training this intern with ROS.
Oof.
Did you have the same experience? Spending too much time equipping your team with ROS skills? Check out our ROS Online training solution for enterprises, a fast and easy way to empower your team with ROS.
From ROS basics to manipulation, perception, AI, ROS2, everything your team needs to learn is here. Practice with real and simulated robots. Train your team by doing from day one. Also, our ROS experts will provide you 1 hour of consulting services to boost your robotics projects.
Want to become a happy Alberto? Request a demo today.